Good evening, everybody. In this video, we are going to discuss about automated diabetic retinopathy detection using CNN. The representatives are Jaya and Khyati. So let's dive into the abstract. So diabetic retinopathy, which is DR, is a prevalent complication of diabetes, often leading to vision impairment or blindness if left untreated. Manual screening of retinal images for DR can be time consuming and prone to errors. This project addresses the need for automated DR detection using CNN, implemented in PyTorch. By leveraging deep learning algorithm, the aim is to develop a model capable of accurately classifying retinal images based on DR severity. The study aims to provide a tool to assist healthcare professionals in early diagnosis and grading of DR, ultimately enhancing patient care and reducing the risk of vision loss. As we can see, this is the normal retina and diabetic retinopathy. Let's dive into the introduction. What is retinopathy? So it basically stands as a formidable microvascular complication of diabetes mellitus, exerting a profound impact on global public health by emerging as a leading cause of vision loss among working age individuals worldwide. As the incidence of diabetes escalates globally, propelled by factors such as sedentary lifestyles, dietary changes, and genetic predispositions, the prevalence of DR is concurrently on the rise. This escalating burden underscores the critical importance of early detection and timely intervention in mitigating the deleterious effects of DR, thereby safeguarding ocular health and preserving visual acuity. Coming to our problem statement, so diabetic retinopathy possesses a significant threat to vision health, especially among the individuals with diabetes, necessitating early detection and intervention for optimal patient outcomes. But unfortunately, the current reliance on manual interpretation of retinal images for DR screening presents several challenges. The process is labor intensive, requiring specialized expertise and significant time investment from healthcare professionals. The increasing global prevalence of diabetes further exacerbates the burden on healthcare systems, exacerbating the challenges associated with manual DR screening. Limited access to trained ophthalmologists and resources in underserved regions compounds these issues, resulting in delays in DR diagnosis and treatment initiation. Therefore, there is a need to develop a robust and reliable automated system that can accurately detect and grade diabetic retinopathy, enabling early intervention and personalized treatment plans. So we took this diabetic retinopathy detecting automation using CNN as a real-world data science problem. So coming on to the literature review, they have several, seminal studies and comprehensive reviews conducted by few of the authors, such as Ting et al., which published the paper was in the year 2017, who introduced a groundbreaking deep learning system as specifically designed for detecting DR and related eye diseases, utilizing retinal image obtained from multi-ethnic population with diabetes. Similarly, another author named Nadeem et al., his paper was issued in the year 2022, who also conducted an exhaustive review focusing on deep learning applications and DR analysis, providing a comprehensive overview of increasing utilization of deep learning in various aspects of medical image analysis for DR, including screening, segmentation, prediction, and classification. And there are furthermore. But right now, jumping to the methodology and results, I like to pass it to Jaya, who can walk us through methodology and results. Jaya, over
Thanks.
to you.
Thanks, Kathy. You can keep scrolling the document. I will be explaining.
Yeah,
Uh,
sure.
Hold on. The methodology adopted for this study encompasses data collection, pre-processing, model development, training, evaluation, and validation. The overarching goal is to design and implement a robust and accurate deep learning model for automated diabetic retinopathy data collection. The dataset consists of a large collection of high resolution retinal images captured under various imaging conditions. A medical professional has assessed the presence of diabetic retinopathy in each image and assigned a rating on a scale ranging between 0 and which correspond to the following: diabetic retinopathy 0, no diabetic 1. These images are annotated with ground truth labels indicating the presence of absence of DR graded on a severity scale. The source of the data set we took from the Kegel. Kegel has a lot of diabetic retinopathy and competitions. Hold on. We took the source, the data set from there. Data preserve. Prior to model development, the raw retinal images undergo pre-processing. The transformation, we use the transformation function to enhance their quality and facilitate model training. Pre-processing steps include resizing image to a standard resolution, normalization to adjust pixel intensity values, and augmentation to increase dataset variability and robustness. Additionally, quality control measures are implemented to detect and remove artifacts of outliers that may adversely affect model performance. You can see the images. The one with the DR. Can you just scroll up? Yeah, you can see the labels: DR, non-DR, no DR. How the images are. So we did the model development. The deep learning model architecture is designed using PyTorch. I use the Jupyter. We use the Jupyter and the PyTorch lib. We install the PyTorch lab using the pip install, and we installed several libraries, and then we started the coding. The deep learning model are in Python is using PyTorch, a popular deep learning framework known for its flexibility and use of use. The model architecture composes convolutional neural network layers, including convolutional, pooling, and fully connected layer. The choice of CNN architecture is informed by prior literature and empirical experiment to identify architectures optimized for medical image analysis. Training. The model is trained using a portion of the data set reserved for training purposes. During training, the model learns to extract relevant features from retinal image, classify them into distinct categories correspond to different states of DR severity. The training process involves iterative optimization of model parameters using backpropagation and gradient descent based optimization algorithms such as ADAM or stochastic gradient descent. We have a function for the training, the model training. We use the ADAM algorithm. Validation. A separate validation set used to monitor the performance of the model during training and prevent overfitting. Performance metrics such as accuracy, precision, recall, and F1 score are computed on the validation set, assess the model's generalization capabilities, and identify potential areas for improvement. Hyperparameter tuning may be conducted based on validation results to optimize model. Evaluation. Once training is complete, the training model evaluated an independent test set that was not used during training or validation. The test set comprises unseen retinal images, aligning for an unbiased assessment of the model's performance in real-world scenario. Performance metrics such as accuracy, sensitivity, specificity, and area under the receiver operating characteristic are computed to quantify the model's diagnostic accuracy and efficacy in DR detection. Implementation and deep learning model is implemented in Python using the PyTorch framework and executed on hardware GPU accelerators to expedite model training and inference. The hardware infrastructure may include high-performance computing clusters or cloud-based platforms with GPU support to facilitate efficient compute. In my case, we used our laptop, the Intel Xeon one, mm, the Lenovo one, the Lenovo laptop, new model. Uh, we ran the process. It took about run the entire program and the images, transforming these images and giving the results, training, and everything took around 31 seconds. I know we used a set of data set. Maybe we used a limited data set, and the epochs we used the 60 epochs. So it it ran in a it it did not took too much of time. I'd say it ran in an efficient way. Ethical considerations. Ethical considerations are paramount in the development and deployment of automated DR detection systems. Patient privacy and data security protocols are strictly adhered to, ensuring compliance with regulations such as the health insurance portability and accountability and the general data protection regulation. Information consent is obtained for the use of patient data in research, and measures are implemented to anonymize and de-identify sensitive information to protect patient confidentiality is the main for all for this, because nobody wants no patient that we don't want to let everybody know about the retinopathy everything. To HIPAA is strongly recommended according to HIPAA. Yeah, it's very confidential. Limitations. Despite the efficacy of deep learning models in medical image analysis, certain limitations and judgment. These include dataset bias, model interpretability, domain adaptation, regularity approval for clinical deployment. Addressing these limitations require interdisciplinary collaboration, ongoing research, and validation in real-world clinical settings to ensure the reliability and efficacy of automated DR detection system. Yes, we need to adopt for different hospital, different clinical trials, and see how well this model identifies the retinopathy, diabetic retinopathy. The trained deep learning model for automatic detection exhibited robust performance. I said it took hardly 31 seconds or 20 seconds across various metrics, demonstrating its efficacy in accurately classifying retinal images based on DRCF. Quantitative one. On the independent assessor, the model achieved an overall accuracy of 51%, indicating its ability to correctly classify retinal image as either positive or negative. And the F1 score is around 63. Furthermore, the model demonstrates high sensitivity and specificity values, underscoring its capability to minimize false positive and false negatives in DR. Diagnostic performance matrix, precision recall, and F1 score were computed to provide a comprehensive assessment of the model's diagnostic. The model precision of 51%, reflecting its ability to accurately identify the positive cases of DR while minimizing false positive. The F1 score is a harmonic mean of precision and recall, Pascal to 61, corroborating the model's overall effectiveness in DR detection. I think I know 51% may not be the great, but above 50% we achieved, but still we need to run more test and validate and tune the model better. Definitely running in different cycles, we can achieve around 90%. I'm confident. The computational efficiency of the model was evaluated in terms of inference, time, and resource utilization. The resources utilized are very not much. Just my laptop I was able to run. Additionally, the model's resize requirement minimal, making it suitable for deployment and low power as a resource constraint. Anybody can run the program on that laptop, I'm sure. We were able, myself and Kathy were able to run on our machines easily with 31 seconds with minimum this thing. We both coded on our laptops only, so I think anybody can run this program on their machine with the images. Go ahead, Kathy. In summary, this study presents a comprehensive approach to automated diabetic retinopathy detection using deep learning techniques, specifically convolutional networks. The developed model demonstrates high accuracy, sensitivity, and specificity in classifying retinal image based on DRC, offering a promising solution. Moving forward, several key next step areas for future research are identified. Firstly, continued validation refinement of the model, as I told earlier, are essential to ensure its reliability and effectiveness in diverse clinical settings. Collaborations with healthcare institutions, regulatory bodies, especially real-world validation studies, and pave the way for the clinical development and more efficient model. Furthermore, efforts to address challenges such as dataset bias, model interoperability, and regulatory approval are paramount for the widespread adoption of automated DR detection system. In conclusion, the developed deep learning model represents a significant advancement in diabetic retinopathy screening, offering a scalable, efficient, and adaptive approach to DR detection. By harnessing the power of AI in medical imaging, the model contributes to early diagnosis and management of diabetic eye disease, ultimately improving patient outcomes and reducing the burden on healthcare system. As research in this field continues to evolve, ongoing innovation and collaboration will drive progress towards a future where automated DR detection is seamlessly integrated into routine clinical practice, ensuring timely intervention and preserving vision health for individuals with diabetes, which is a key factor. The vision is a key factor for diabetic people. As the diabetes increases, the vision is the first one which gets affected. So I feel this project is a we took this project as a capstone project, real world data science problem, mainly because of the diabetes and how it impacts on the eye health. Go ahead. Kathy, go ahead. Go on. So we have the references we listed, and also go on. We give the appendix. The Kaggle I took from the Kaggle, and also the appendix. We have our code both on the GitHub, open to public. People can easily take a look at it. Thanks for listening. And this is our capstone project for MS in Data Science at CUNY. Thanks, Prof, giving us an opportunity and guiding us to select the good project to showcase for the capstone.